Hello guys and welcome to plcgoods video tutorial. In this video I will review basic data types and explain array tags and the file Misc group of instructions. Shift and sequencer instructions work with array tags. In this video, this virtual controller will be used to test instructions. First, let's have an overview of the basic data types and how an array tag can be created. Tags can be created inside the program tags or controller tags tables. We can access all valid addresses of modules in the controller tags table. Also, we can create tags to store and use data on a PLC memory. The simplest data type of tags is Boolean. It uses one bit, which can be 0 or 1, so it can be used to represent only two states. Another data type that can be selected for a tag is integer. This data type uses 16 bits to store integer numbers from minus 32,768 to plus 32,767. If we need to store a larger number, the double integer data type can be used. The data type uses 32 bits to store a signed integer number within this range. Similarly, a tag whose data type is real uses 32 bits to store floating point numbers based on the IEEE standard. Note that there are many data types. We used some of them during this tutorial like timer, message, and alarm. For instance, a counter instruction uses a counter type which has 7 parameters, 2 parameters to store 2 double integer numbers and 5 Boolean addresses to represent the counter's state. Now let me show you another example. I want to use a GSV instruction to store my controller's time. I can use an SSV instruction to change it. I need to create a tag to store the local data time attribute. Let's search for that on the help window. This parameter includes 7 numbers in double integer format, which are year, month, day, hour, minute, second, and microsecond. Let's select a new tag as the destination address. Now let's select DINT as the data type and enter the number 7 to create an array with 7 elements. Then let's refer to the first element of the created array. Now the GSV instruction will use the first element with this address and the next 6 elements to store the date and time on the created array. Let's download and test the program to see its result. Here is the created tag. Let me click on the Monitor Tags tab to see its value. Now I can see the current time of my controller. Note that this type of data is called an array. Arrays allow us to store a group of data of the same data type by the same name, but we can use a number or an index to identify an individual element. Now let me define another array. When we define a new tag, it does not have any dimensions by default. I can click here to change its data and dimensions. For instance, let's have an array or a vector with 10 elements. I can add another dimension to have a matrix of the same data. Let me define another array with the same size and delete unnecessary tags. Let's open the help window and search for arrays. Here you can see a description of arrays. These figures can help you to understand how a group of data is stored inside an array which has 1, 2, or 3 dimensions. For instance, this 3-dimensional array with this size can store 24 double integer numbers. Let's start learning the file Misc group of instructions. These instructions operate on arrays of data. The first instruction is FAL, or File Arithmetic and Logic. Let's see its description on the Help window. This instruction performs copy, arithmetic, logic, and function operations on data stored in an array. After the description of each parameter, here are some examples of using the FAL instruction. For instance, this instruction can copy each element of an array into the same position within another array, or copy one value into specified positions. Also, it can do an arithmetic or logic operand between two groups of data and store their results on another array. Let me write and test a simple program with this instruction. First, I should create a new tag whose data type is control. It has some parameters. You can see each parameter description on the help window. Then I need to determine how many elements in an array must be manipulated. The next parameter displays the current position in an array. By default, its value is 0. I can select ALL or increment items for the next field or enter a constant number. Let me select the increment mode. I will explain the other states later. Now I should determine a tag to store the result. This address refers to the first element of tag 6 whose data type is an array. Instead of using a constant number like 0, let me use the position address which FAL instruction increments it. I want to multiply each element of tag 7 by number 2 and store its result on a destination address. Similarly, let me use the position address which a FAL instruction uses. Let me use a normally open contact to enable the instruction. Based on this program, when I use a contact to activate the FAL instruction, the position parameter will be incremented by 1 unit and this expression will be calculated and copied to this address. Let's download and test the program. Let's have a better view to see the program and the defined tags. Now let me change the stored numbers on tag 7. I can right-click on the Enable Contact and select Toggle Bit to change its state, or press Ctrl+T on a keyboard. By each activation, the position parameter is incremented by 1 unit, and element of tag 7 is multiplied by 2, and the result is stored on the element of tag 6. Note that after the fifth activation, the position starts from the first element. The first 5 elements of tag 7 are multiplied by 2, and its result is stored on tag 6. Instead of an INC or increment mode, I can enter a constant number or select the ALL mode to calculate all expressions and store all results by the first activation. The second instruction of the file Misc group is FSC, or File Search and Compare instruction. It compares values in an array element by element to return an array position where the instruction finds a true comparison. This instruction works like the FAL instruction. Let's see the next instructions. The copy file and fill file instructions work similarly. For instance, the FLL instruction fills elements of an array with a source value. Also, I can use a constant number as a source value. Let's use the fill file instruction to fill these elements of tag 6 with number 25. Now let's open the controller tags table to activate and enable contact. These elements of tag 6 are filled with number 25. The file Misc group of instructions operate on arrays of data. Let me explain other instructions briefly. The average instruction calculates the average of a set of values. The sort instruction sorts a set of values in one dimension of an array in increasing order. The std instruction calculates a standard deviation of a set of values in one dimension of an array and stores a result in a destination address. The array size instruction determines size of an array. The CPS instruction copies the values in a source to a destination address. Note that, like the file Misc group, the file shift and sequencer groups of instructions work with arrays too. We can use the file shift group of instructions to modify a location of data within arrays. We can usually use sequencer instructions for repeatable operations. Now, after a short review, we are going to use FFL and FFU instructions to do a simple warehouse project. I already explained an array tag structure and some instructions from the file Misc group. These three groups of instructions, file Misc, file shift, and sequencer, work with arrays. We are going to use the FIFO Load and FIFO Unload instructions to do a simple project related to a warehouse project. So let me explain how to use these instructions using the help window. First, I must define an array like this one to store numbers. Sometimes a part of memory which is used for the FFL and FFU instructions is called a stack. The FFL instruction loads new values into a fresh free position in a stack memory. The FFU instruction works inversely. When we use a FFU instruction for a stack memory, which is an array, a PLC moves its first value to a destination address. Then it shifts all data one element inside the stack memory. Now let me test the final project. After that, I will explain how it can be done in Factory I/O. Okay, my project is related to a warehouse. Here are 54 places to store some boxes. I can access each place with this stacker crane. Let's see how we can control it. This crane has 3 digital actuators. Let's change the controller mode to run mode. I can move the crane up and down with the first digital input. Also, I can use the crane arms to move boxes to a left side with a second digital input. Similarly, the crane arms can be moved to the right side by the third digital input. In this project, I used the fourth digital input to activate this emitter to drop a box with its pallet on the crane arms. Now let me move the crane arms to their default positions. Note that the stacker crane has 4 modes. I selected the numerical mode. In this mode, the stacker crane accepts an integer number from 1 to 54 related to each position on the racks. I can select a desired position using this potentiometer, which it is going to be a number from 1 to 54. After that, I can press this push button to store it on a PLC memory. This can be repeated up to 5 times to store 5 positions on a PLC memory. I used FIFO Load and FIFO Unload instructions to store desired positions. Eight is the first desired position. So when I press this push button, the crane will go to this position and it will be cleared from a PLC memory. It will be replaced with position 1. I used a FIFO Unload instruction in my PLC program to move selected positions on the stack memory. Let me press the red push button. Now I can use the digital inputs to control the crane to place a box on a desired position. Note that number 55 refers to the initial position of the crane, where an operator can place a box on the crane's arms. So let me press the 5th digital input. I used it inside the PLC program to select number 55 as the destination of the stacker crane. Let me place another box with its pallet on the crane's arms. Now if I press the red push button, the crane will go to the first position. Now let me place a box on the first position. Until now, the crane went to the first two positions, and there are three positions on the stack memory of the PLC. Here you can see how some positions can be stored and used on a stack memory. Now let me show you how this system can be designed inside Factory I/O. First, let's insert a stacker crane from the right list and select the numerical mode for the crane. Then let's insert 3 racks. Obviously, these 3 racks support 54 places to store boxes. Now let me insert an emitter from the right list. Here I determine which type of boxes can be entered. I press the V key on the keyboard to use my mouse to change the height of the emitter. The emitter is in forced mode and it is enabled to enter boxes. I can disable it or connect it to my controller. Also, the crane has 4 actuators which I will connect them to my controller. Note that the crane has 4 sensors to detect its state. They can be used to control the crane automatically. In this video, I will use only the actuator tags in the program. This plant is not connected to the controller, so I need to control them manually from here. Later, I will connect these 4 actuators to the PLC outputs and write a program to turn them on or off using 4 digital inputs of my PLC. This is the main actuator with this tag. It can accept an integer number from my controller. Now let me write number 3 manually and test it. Obviously, the crane is moving to position number 3. Other positions are accessible by entering a number from 1 to 54. If I enter number 0, the crane won't change its position and I need to enter number 55 to get it to its initial position. Now let me design a simple control box to enter a store and to display 5 positions. First, let me insert a potentiometer. I will use it to select a number from 1 to 54. The potentiometer's voltage range is between 0 and 10 volts, so I must multiply it by 5.4 in my program. Then, to convert it to an integer number to display it on this digital display. Also, let me insert 5 digital displays to show the stored positions on the PLC memory. Now let me add some push buttons. Note that the red push button is a normally closed one. There are 6 digital displays on the control box. Let's define suitable tags for them. Now after selecting the controller type, I should determine my controller IP address and its slot number. After that, I need to define some suitable tags to use in the program. Based on these settings, these tags are created. Let me connect each equipment to its related tag. First, I connect the push buttons and the potentiometer as my virtual PLC inputs. Then let's connect the first 3 digital outputs to 3 digital actuators of the crane and the fourth one to the emitter. I will use 4 real digital inputs in my PLC program to activate these actuators. There are 7 outputs with an integer data format. 5 of them are connected to 5 digital displays. The 6th output sends an integer number to the stacker crane to change the crane's position. The last one is used to display a selected position by the potentiometer. The next step is to define these tags in RSLogix 5000 to use them to write the program. Note that tags must be defined in a controller tags table. Now let me explain the program. At the first run, I use the multiply instruction to convert a received voltage from the potentiometer to a number between 0 and 54 to show the result on a related display. At the second run, the first push button enables this FIFO Load instruction to transfer a selected position by the potentiometer to a PLC memory. Here I use this tag. Its data type is array with 10 elements, but only the first 5 elements are displayed by these 5 digital displays. Here I used 5 move instructions to send the stack memory values to the 5 digital displays. Here, based on the program, if I press the second push button, the FIFO unload instruction transfers the first element of the selected array to the crane to change the position of the crane inside the factory I/O. The next RSLogix is simple. I used 4 real digital inputs to control the crane, the emitter, and a real digital output as well. Finally, I used the 5th digital input to move number 55 to the crane to move it to its initial position. After transferring the program to the PLC, I need to connect factory I/O to the controller. Now I can test the project, which I did it already. Now we are going to learn the program control group of instructions. We will start with the jump and label instructions. Also, we will see what the no operation instruction is. After that, we will see how subroutine instructions can be used to repeat a program many times. Then I will explain the TND and MCR and the interrupt instructions briefly. Then I will explain how a program can be executed based on a specified event. After that, we will learn an AFI instruction. Then we will continue learning program control instructions with the sequential group of instructions. Then we will do an automatic warehouse project in factory I/O. I will use this virtual PLC station that it is already configured inside RSLogix 5000. First, let's select the program control group of instructions. Here is the jump instruction. This instruction and the label instructions work together. First, let's create a label. Now I can select it for the jump instruction. These two instructions skip a portion of my program. Let me modify the program a little. Between the jump and label instructions, here I can add some more runs and any other instruction. Let me use a NOP instruction from the program control group. The NOP instruction does not do anything, but it can remove this error from the program. Based on the program, if I enable the jump instruction with this contact, the PLC starts the program execution from here. So the controller won't execute this part of the program. If I don't activate the jump instruction, it does not affect the program execution. The JSR jump to subroutine is the next instruction. I used it to call another routine. The JXR instruction or jump to external routine works like the JSR, but it executes an external routine. Note that this instruction is only supported by SoftLogix 5800 controllers, so let me skip it. The next instructions are RET and SPR, which are usually used inside the subroutine. So we use these instructions when we want to have a subroutine. Let's learn an important application of these instructions. Suppose we need to calculate the coefficient of variation many times in a PLC program. That is defined as the ratio of the standard deviation to the average value of some numerical data. This parameter is widely used in analytical chemistry and commonly used in fields such as engineering or physics. I can write a program in 4 runs to calculate this parameter. Here are two choices: repeat its program, which includes 4 rounds, or write it inside the subroutine and call the subroutine as many times as we want. Now I create this subroutine and define it as CV and use the JSR instruction to call it. The CV subroutine needs to get some numerical data to return their CV value. So let me open the program tags table to define some tags. Let's define two arrays including 5 elements to store numerical data and two tags whose data type is real to store the result. Let's open the main routine and use the JSR instruction to send the numerical data in array 1 to CV subroutine and store its result on CV1 tag. Now the JSR instruction sends stored data on the array 1 to the CV subroutine and stores the result on the CV1 tag. Now let's write a suitable program inside the CV subroutine. First, I use the SPR instruction to get array 1 data and store it on an internal array like A. Now let me use the std instruction to calculate the standard deviation of numerical data in the first dimension of the internal array A and store the result on a tag like std. Note that the A tags include 5 numbers. Let me use the average instruction to calculate an average of the numerical data. Now in the next run, let me use a div instruction to use these results to calculate the coefficient of variation. Now I need to determine which parameter should be sent to the main program routine. So in the next run, let's use the return instruction and select this tag as the program result. This program calculates my desired coefficient of variation. There was only one small problem in my program I noticed after testing it. Here, the number 5 must be entered in the length field, not in the position field. The CV routine calculates and stores a desired coefficient of a variation on the CV result, then it sends it to the main program routine. The main program receives the result and stores it on the CV1 tag. Now I can use the CV subroutine to calculate the coefficient of variation for another set of numerical data without writing its program again. I only need to change its input and return parameters. Now let's test the program. I forgot to define this tag. Also, let me modify the previous problem then download the program to my PLC. Now let me change numerical data on the created array tags. On the first array, I entered 5 numbers that are close together. For the second array, I entered 5 numbers that are very different from each other. So I expect the coefficient of variation of the first numerical data to be less than the second one on the second array. Now these tags CV1 and CV2 are equal to 0. Based on the program, let's use the enable contacts to call the CV subroutine to calculate CV1 and CV2. Obviously, the CV1 value is less than the CV2. I hope you learned how to write subroutines and to use them inside of your main programs. Note that we only need to change its input and return parameters. Now let's see the other instruction of the program control group. These instructions are simple. TND is a short form of temporary end. When the controller reaches a TND instruction, a controller moves to the end of the current routine. The MCR instruction is used in pairs to select a zone of a program. We can disable or enable all runs in the selected zone with 2 MCR instructions. The UID and the UIE instructions work together. We can use them to enable or disable interrupts, usually for critical parts of our program. These 3 instructions are related to a sequential programming that I will explain and use them in the next video. Now let's see how the event instruction works. It works like the JSR instruction, but it calls another type of task. Let me create a new task. Now let's select the event type inside the type field. So when a trigger condition happens, the new task will be executed once. Let me select module input data state change item. Then I need to determine a tag from my modules. Based on these settings, when an input module has any changes in its state, a new task is executed once. Overall, there are 3 modes for each task. The main task, which is usually used to write a PLC program, is continuous mode. My PLC executes that continuously. A periodic task is executed periodically, and when the event mode is selected, PLC executes the task when a specific event happens. Now let me create a new program folder and a new routine inside of a new task to write a simple program. Let me write a simple program inside this routine like this and download it to my virtual controller. If I change any input address of the input-output module, this program will be executed. So based on the first run, if I change any input address, the first digital output will be on. But if the first digital input is activated, the controller will turn off the digital output. The main point in this simulation is the controller doesn't execute this program continuously. It executes this task and its program once when it detects any changes at the input address of this module. Now let me create another task whose type is event, but let's select the event instruction only choice as its trigger option. Let's create a program folder, then create a routine for the new task. Inside this routine, I can write any program. This task and its program are executed only by an event instruction. So let me add an event instruction inside the main routine of the main task. Now let's use an event instruction to call the task in which the event instruction only option is selected for that. Now let's use a one-shot instruction. So based on the second run, if I activate this contact, this task will be executed once. The next instruction of the program control group is AFI or always false. Now the JSR instruction is executed based on this contact. If I remove this contact, the JSR instruction will be executed during all scan cycles. But if I use an AFI instruction before that, the controller won't execute the JSR instruction. I explained all instructions of the program control group except these instructions which are related to the sequential programming. Now we will have an overview of Sequential Function Chart or SFC programming language. First, I will explain the three basic languages briefly. Then I will write and test a simple program using the SFC language. After that, I will explain three instructions of the program control group. Finally, I will do a practical project for implementing an automatic warehouse system. Before explaining the sequential instructions, let's have an overview of the three basic PLC programming languages. When we create a new routine, we can select its programming language as well. Until now, we were using the ladder diagram language. Another programming language is FBD or function block diagram. For instance, let's see how an add instruction can be implemented in the FBD language. I want to add a stored value on tag A to a constant number of 25. Now let me store the result on tag B. This is a simple program in FBD language. Here are instructions to use in FBD language. Now let me create another subroutine using a structured text language. For instance, let me use a jump to subroutine instruction to call R1 subroutine. Each instruction has a specified text or code. You can write them directly or select them from here. Ladder diagram, function block diagram, and structured text are the three basic programming languages. Here is another language, Sequential Function Chart, which uses the three basic languages. SFC is a graphical programming language that displays the process flow as a diagram, thereby allowing a user to control sequential processes by describing the transition conditions and actions for each step. Now, here is one step and its transition condition. Let me extend it to 3 steps. From here, I can add steps and transitions to my program. At the end of a process, I can stop it with the stop instruction or connect that to another step. Note that always one step is selected as the initial step and the type of other steps are normal. Right now, I selected the first step of my program as the initial step. I don't want to do any action inside the first step. Let me skip it. Then I need to determine its transition condition. The transition condition determines when the controller should exit from the first step and execute the next one. Let's use the first digital input address as the first transition condition. If I activate the first digital input, this tag tran0 changes to 1. Then the controller executes the second step. Now let me define an action for the second step. Here I can write the program of my action in a structured text language. It is a little hard to write a program in this small box. I can also call a routine that includes my program using the JSR instruction. So based on this program, when the controller is at the second step, it executes R1 subroutine. Note that R1 subroutine can include any program in any language. Similarly, let me call another subroutine when the controller is at the last step. Also, let me use the second and third digital input as the transition conditions respectively for the second and third steps. This is a simple program in SFC language with 3 steps and 3 transition conditions. The controller will execute the whole program because I connected the last transition to the first step. Note that I wrote this program inside R3 subroutine. So let me call that from the main routine. Now let me download and test the program. The controller enabled the first step. If I activate the first digital input, it will go to the next step and executes its action. So, based on my program inside the first action, the controller calls the R1 subroutine. Now let me activate the second digital input to exit from the second step and go to the third step. Note that here, by a mistake, I entered the address of the first digital input instead of the third one. This address is also used for the transition condition in the first step. So when I activate the first digital input, the controller goes to the first step and then it immediately goes to the second step. I hope you learned how a sequential process can be programmed using the SFC language. Now I can explain 3 instructions related to SFC programming in the program control group of instructions. The first instruction is SFR or reset SFC. This instruction resets the execution of an SFC routine at a specified step. My SFC program inside this routine has 3 steps, so I can change the step which is executing with the SFR instruction. The next instruction is SFC pause or SFP. This instruction can pause or restart an SFC routine. I will use this instruction for the next project. The third instruction is EOT or end of transition. This instruction returns a Boolean state which is equal to its previous run condition to change a transition condition. SFC programming language and related instructions can help us to control sequential processes like controlling this warehouse. I want to use SFC language to fill racks automatically. Let's test the final program. The crane gets boxes automatically and it finds an empty rack position to place them. Note that this process can be divided into some steps which should be repeated. This is my final program. It includes 9 steps. Obviously, each step is executed after its previous one. Now let me explain the system and the program. Note that I explained this system in lesson number 28, but here there are 2 important differences. First, I modified the control box. It has only one display to show an empty rack number and 2 push buttons to stop and restart the program. The second point is using sensors. We used these actuators in lesson number 28. Each actuator has a sensor to allow the controller to detect the current state of the stacker crane. The state of this sensor is 1 when the crane is changing its position. The controller can use these 3 tags to detect the crane arm positions, which are right side, middle, or left side. Now the middle sensor is activated. Finally, this tag is equal to 1 when the crane is moving in the vertical direction. Let me test the last sensor. If I activate this actuator, this tag is equal to 1 during the crane's movement. This is the PLC program. The main program calls the SFC program, which includes 9 steps. Each step uses a JSR instruction to execute another subroutine. Also, the second and third rounds of the main program use start and stop push buttons to execute and pause the SFC program. I divided the sequential process into 9 steps. Each step calls a routine and has a transition condition. The first step calls the first subroutine. Here I move the crane to its initial position and turn off all actuators. Then if the crane is not moving and the middle sensor is activated, the program enables this tag. I used it as the transition condition for the first step. The second step calls the second subroutine. It only opens the crane's arm to a right side until the right limit sensor is activated. The third step enables the emitter to drop a box on the crane arms. Also, it enables a timer. After 1 second, the done bit of the timer activates the fourth step. Step 4 disables the emitter, resets the timer, and moves the crane arms to their default position. The controller exits from this step when the middle sensor of the arms are activated. In the next step, I defined an array with 54 elements, respectively, for 54 available positions. I used an FSC instruction to detect an empty position. If it detects an empty one, then the detected position is displayed and the crane goes there. Also, this position is saved on the related element of this array, and the controller lifts the crane upward while it's moving to a detected position. The program enables the next step when the crane starts moving. During the crane's movement, program only resets this bit of the FSC instruction. Otherwise, it won't look for another empty position for a next box. When the crane reaches a detected position and it stops, the next step, step 7, opens the crane's arms to the left side. The program executes the 8th step when the left limit sensor is activated. Now the controller lifts the crane downward and closes the crane arms. Then the controller moves the crane to its initial position. Also, the controller goes to the first step and it repeats this sequential process to get and to place another box on an empty rack. Let's test the program again. This is the array with 54 elements that are used in the FSC instruction. Some elements of the array were filled and I am filling some elements manually. Right now, the first empty position on racks is element number 10 and after that element number 13. Now let me press this push button to resume the process and see the performance of the program. The controller will detect empty positions successfully. The crane will go to position number 10 and after that to position number 13. The controller continues filling racks process until there isn't any empty one. Now let me pause this process using the second push button. Until now, we learned basic and some advanced instructions in RSLogix 5000. Obviously, after the program control group of instructions, there are also some other advanced instructions. Some of them are explained during this tutorial. In the next videos, we will see how an HMI device or human machine interface can be connected to a controller to help us to monitor and to control a process. Thanks so much for watching.